Um, All right, everybody, how are you guys doing? Well, I guess I can't ask that because you can't talk back to me, but that's irrelevant. I'm Arya Rao from the Science Squad, and thank you so much to David Klinger, who came in today on really, really short notice when our other mathematics professor, Dr. Jerome Troba, dropped out at the last minute, and that's all right, but we've got David Klinger today talking about cardinality, so I'll hand over the reins to him.
Hello. Okay. I'm David. I'm a third-year math major at the University of Chicago, and I was asked to come on and talk for 7 to 10 minutes about a math topic of my choice. So I decided to talk about the thing that when I was sitting in math class and they told me, I was like, yeah, this is exactly, I would like to be a math major now. Anyway, so this is about sets and how we can know the size of a set. So essentially in math, we have this concept of a set, which is just something with something else in it. You could have a set of potatoes, a set of animals, a set of people. Most commonly, we use a set of numbers. So here are 3 examples of sets. We have 1, 2, 3 in squiggly brackets. So that's a set just containing 1, 2, and 3. We have fancy Z, stands for something in German, but it means the integers. So you see I have dot, 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 comma, -1, 0, 1, dot, comma, dot, 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 squiggly brace. So that means the dot, dot, dot means just continuing in this fashion. So we have 0, -1, -2, -3, and then going on and on and on as far as you can count. And we have 1, 2, 3. You can see that's an infinite set, but it's still a set. There's no limit saying that a set has to be finite. We have another kind of set, and that's fancy n, the natural numbers, or the counting numbers. 0, 1, 2, 3, 4, 5, 6, any number you can count to. You'll notice that the naturals is a subset of the integers. Any number that we can count to is also an integer. So 0 is an integer, 1 is an integer, 2 is an integer, etc. Now, how can we say that one set is bigger or smaller, the same size as another? When you just have finite sets, it's very obvious, right? Because if you have one set with less elements than the other, and one set with more, then it's very clear that one is less, one is more. What about with infinite sets? Can you have one infinite set that's smaller than the other? For example, naturals is a subset of integers. Does that mean that the naturals is actually a smaller set than the integers? So obviously, we can't just count every element in the integers, because that's impossible. There's infinitely many. We'll be counting forever, literally. So to get around that, mathematicians had to learn how to count like 5-year-olds. Now, 5-year-olds can't count, but they can tell when things are bigger or smaller. Imagine you have two large jumbles of blocks, and you want to know which is larger than the other, and you can't count. How could you do it? Well, if you've ever seen a 5-year-old do this, they'll stack them on top of each other and make another pile, stack them on top of each other, and they'll just compare which is larger. So I drew a little picture. My 2 stacks of blocks, we can see very clearly that one is smaller than the other, and we can see that without even counting. It doesn't matter how many elements are in there. When we pair it up, we can very quickly see if one set is larger than the other. If we can find a pair between all elements of the set, then they have to be the same size. If sets, not just blocks. So for example, I have 2 sets down here, A, B, C, D, and 1, 2, 3, 4. And I drew pairings. I paired A to 1, B to 2, C to 3, D to 4, etc. And there you can see that the sets must be the same size because we paired it up. As it happens, you can do this with infinite sets too. And even crazier, you can do this between the naturals and the integers. Here I've managed to pair up the naturals and the integers. 0 to 0, 1 to 1, 2 to -1, 3 to 2, 4 to -2, 5 to 3, and you can keep going. 6 to 4, 6 to -3, and you can go through and you can pair every single natural up with an integer, which gives us that the integers and naturals are the same size, even though one is a subset of the other. It's crazy. Anyways, you can even find an explicit rule. Here, I wrote it out. We have f from n to z, which means that our function f is taking elements of n and giving us elements of z. So we can give in any natural, we'll give it an integer. And I wrote it, okay, f of n equals n plus 1 divided by 2 if n is odd, and negative n divided by 2 if n is even. And that rule just describes the pairing I wrote up, and we can actually analyze it to see that it is both one-to-one and onto. It is both a surjection and an injection, which means it's a bijection, which is the fancy math word of saying you take two elements, you can take every element and pair it up. Now, what about an even crazier set? What about Q? So Q is the set of all numbers that can be written as A over B, where A and B are integers. So examples of, so Q means rational. So like 0.33333, 1/3. That's not an integer, but it is rational. 152 over negative 375. That's also a rational number. Now, what's crazy is this actually is the same size as n and z. And look, here's how we can see it. So what I did here was I made a grid with 0, 1, -1, 2, -2, 3, -3, ... 0, 1, -1, 3, -3, ... So basically, I wrote out a multiplication table, and instead of actually multiplying it, I just wrote down the combination. So when we have 1 and 1, we get 1 over 1, 1 over -1, and so on for every single combination of these numbers. And it's pretty clear to see that if we extended our grid out forever, we would have every single rational number. And now look, we can actually list it. First element will be 0, next element will be 1, then 1. And anytime we have repeats, we'll just like consolidate them. So we'll just skip it. But 1, okay, skip that. -1, skip that. -1, skip that. And we can just keep going through, and you'll see that we can finitely, by drawing diagonals, they'll get bigger and bigger, but every diagonal we look at will be finite. And we can count them all off in a line. And I won't write out the explicit rule for this because it's a lot more complicated. But basically, Q is the same size as n and z. Oh, and once we've established that, okay, so if we have two elements that we've shown are the same size, we call that cardinality, by the way. If we have two elements that we've shown have the same cardinality, then we can just use the transitive property. If A and B have the same cardinality and A and C have the same cardinality, A and B and C. So now you might be wondering, okay, is every single element have the same, does every single set have the same cardinality? Is every single infinite set, can you somehow like count it this way? And the answer is actually no. So the finding cardinality between a set and n, we call that a countably infinite set. And that's a very special kind of infinite. In fact, it's the smallest kind of infinite you can find. So I'm going to show you an example of a set that you've probably heard of that is actually not countably infinite. And the proof of this is incredible. So that set is R. R is literally any number you can count to that is not imaginary. So perhaps I'm sure some smart person will find a way to break my very non-rigorous definition. But an example, pi. Pi you cannot write as two integers over each other. Or square root of 2, you can't write that. That actually has a really cool proof too. You should look it up. But basically, anything that has a non-repeating decimal representation, that's going to be irrational. You can't show it as Q. That you can't show it as the quotient of two rationals. But it's still in R, our real numbers. Now, so we're going to show that our reals are not countable by going through just 0 to 1 and showing that 0 to 1 is not countable. So what we're going to do is list out a list Well, we're going to suppose, for contradiction, that we can list every single element of the reals between 0 and 1. And it's very clear to see that if you can list it, then it must be countable, because we just make the first element 0, the next element 1, the next element 2, the next element 3, and go on. So, okay, so 0 point A11, A12, A13, A14, on and on. Okay, 0 point A21, so digit number 2, digit 1, A21, okay, digit A22, the second number, the second digit, A23, A24, on and on, A22, A31, A33, A34, and we just continue like that infinitely. So 0 point, each A is a digit. So we have every digit, every number, every real number written out in its decimal form and countable, except we can prove that our list is necessarily non-complete. We're going to make a new number, and we're going to call it B. We're going to make it such that BNM equals 3 if Bn equals 3 if ANN does not equal 3, and 7 if ANN equals 3. So what we did here is we're going to make a new number, and we're going to construct it by saying, okay, first number, B1. Well, let's look at A11. What is that number? If it's not 3, then we make it 3. If this number is not 3, then we make B1 a 3. If it is a 3, then we make B1 a 7. Okay, now we go to B2. We look at, okay, A22. Is it a 3? Then we make it, if not, we make it a 3. If it is, we make it a 7, etc., etc. So what you'll see is that the first digit has to be different from the first digit of the first number. The second digit has to be different from the second digit of the second number. The third digit has to be different from the third digit of the third number. The fourth digit has to be different from the fourth digit of the fourth number, and so on. And what we've now shown is that every single digit is going to be different than at least one digit in every single number that we've written in our list. So this new number, made of all our B digits, must not be in our list. So this could not have possibly been a comprehensive list of every real number. Z, R, and Z, Q, countable, all have the same cardinality, are all the same size, but R is actually somehow larger. We also have this crazy idea that when you have infinite sets, and a set that has contained within another set can still be the same size, even though it seems impossible. Anyways, this is just a case where the math is right and reality is wrong. So I hope you all consider doing theoretical math, and thanks for listening.
All right, everybody, thanks for watching, and more importantly, thanks to David for coming on and talking about cardinality for us. So if you have any questions, you can feel free to email the Science Squad or contact us through social media or comment in the video, and I'll be sure to relay those to David and have those answered for you. And hopefully see you next month. Bye.